Welcome to this interview. I'm David Katzmeyer from the United States, here with Ray Tomes in Auckland, New Zealand. We're here in his home. We're discussing a series of points on the study of cycles. In this discussion, we're going to be talking about the fundamentals of the universe. Thank you, Ray, for this discussion. Ray, start us off a little bit here. We know that cycles are within cycles within cycles. Cycles are in everything. They're within us and they're without us. And as we look at the macrocosm in subatomics and the macrocosm of astrophysics, we find that cycles are within, around, and through everything. So how do we make heads or tails of all of this, Ray? How can you tell us a little bit something about the fundamental workings of the universe?
Yeah. Well, I had a curiosity about a lot of these things, but it was cycles that got me on a path that made me believe I could understand things at a more basic level than I think other people had before. And the reason was that it came about through harmonics theory, which predicted that there were different scales of structure in the universe at ratios of about 30,000 in spacing, so that what we would call the Hubble scale, the observable universe, that the galaxies, the spacing of them was about that division of the Hubble
30,
scale.
60, 90, so
30,000 odd. And then the spacing of the stars was about that much smaller again, and the spacing of the planets that much smaller again, and the moons that much smaller again. And the next couple there's nothing obvious, but then you get to cells, and you get to atoms, and you get to subatomic particles. And all of these fitted these fairly regular spacings that were predicted by the harmonics theory. And so at that stage I decided there's got to be one fundamental law that runs it all. Now people like Einstein and others had worked on this, trying to find a wave equation or some sort of equations that would work for the whole universe. And they had limited success because they couldn't get it to combine all the things. But with cycles, we actually can realise that it definitely is one thing, because there are examples from as large as 600 million light years spacings right down to human size, and even the atomic realm, where we know that there is a wave that has a wavelength and a period that match if we assume that they propagate at the speed of light. So what that means is all these phenomena are of the same type. They are to do with electromagnetic fluctuations, electromagnetic waves. There are vast electromagnetic standing waves in the universe. If they're not electromagnetic, then they might be gravitational, which also moves at the speed of light, but they're definitely speed of light waves. Some form of those waves is explaining the structures, all of these structures in the universe. And so it was that made me realise that if that's the case, and it's working through all those things, then at the atomic realm and at the particle realm, it must be the case that those things are standing waves of electromagnetism. Now, I have an alternative form that I prefer to think of them. I prefer to think of them as waves in the ether, and that there's just standing waves, and that particles, basically what you've got, a particle, they have this duality, the wave and the particle. What I'm going to say is there is only a wave. What the particle is the centre of where the wave converges. And in fact, I first began to think of the form of that when I was having a cup of tea and I put it down. And when I put it down, I noticed that a circular wave pattern came in from the edge of the cup of the tea to the middle.
Yes.
And as it came in, it got stronger because it was concentrating.
Yes.
And I jiggled it up and down, and when I got exactly the right frequency, you could get this wave going really well, until I got exactly the right frequency too well, and a jet of hot tea hit me in the eye. At that stage I decided I need to be able to control this experiment better.
Yes.
And I made a little circular dish that I put on the speaker on my computer, and I played sounds of different frequencies through it and different volumes, and I recorded it. And we'll have a separate talk about it at some stage, and it overlaps with the area of cymatics. And I believe I found things there that showed what is the nature of atomic particles, and what is the nature of charge and other things. But put that aside, and let's just say for the moment that what I think a particle is, a standing wave, is a spherical wave coming in to a point, which is the centre of where we say the particle is, and then as it passes through the centre it comes back out again. And that the wave, if you have a travelling wave in each direction, it makes a standing wave. So you would have had a wave that was doing this along, and you had another one doing it in the other direction, and they combine to make a standing wave that's just doing this.
Well, Ray, I want to ask you right at this point. You mentioned a standing wave and a traveling wave.
Yeah.
Okay, we're all familiar with what a wave is, but not all of us know what's the difference between a standing wave and a traveling wave.
Well, if you have a pond and you drop a stone in it,
Yes.
a wave goes out. That's a travelling wave. And that's the sort of wave that we think of light as being, and so on. And sound. We make a sound, and out it goes.
Okay.
A standing wave is one that keeps on repeating. Like a guitar string. You pluck the guitar string, it oscillates in place. You can flick one end and get that sort of thing to happen, but it will bounce off the other end and come back.
Yes.
And it will actually make maybe a wave with multiple
Stopped at
things
both
in
ends.
it.
It's within the containment.
Yeah. Now the containment for the standing waves of particles is the centre, where it passes through, and the rest of the universe. Not very contained, is it?
So is more than one wave coming together to form a particle? Converging with other waves at a point?
Well, an electron is probably just one wave. A proton is more complicated.
Okay.
But the basic idea is that what I'm going to propose, you can do it with electromagnetism. So people that have an objection to me using the word ether, and I know there's a number of reasons people have objections to that, they can all be shown to be based on misunderstandings of physics, that they can be all got rid of, the objections. And so my preferred form of thinking it is there is an ether. And the way I think of it, it's like what we call jelly. Now, it's not what you call jelly, which we call jam. It's what we call jelly and you call jello, right?
Right.
So everyone should be clear about that. We have a bowl of this stuff.
Yep.
And it's nice because in human timescales we give it a wobble, and this will sit there wobbling about, right? And we can see the wobble of it. We can see the waves in it. We can do the same thing with a block of steel. We can hit it with a hammer, but the waves in that, it'll go, and the waves are so fast we can't see them. We can hear them,
Yes.
but we can't really know what's going on. With jelly, we can see what's going on, and we can see the wobbles. Now, I think of the universe. I used to write a blog called Wobbly Universe.
Yes.
And the bowl of jelly symbolises that. The blob of steel does as well. But as we move from the slow wobbles of the jelly through the very fast vibrations of the steel, in the universe they're that many times faster again, because the vibrations, the speed of sound in the universe is the speed of light. Right? The way light is the sound of the universe. Well, it's the light of the universe, but comparing it to these other ones, the waves that happen at the speed of sound in there, light is much faster. So that's what's going on. Now, if we think of the ether, there's a certain number of different things can happen with it, but the basic laws of it are very simple, and were explained by Maxwell, and he made some wave equations, and the basic thing of it is very simple, that when you displace it a bit, it creates a tension there that tries to pull it back again, right?
Okay.
And that it's got some momentum, so when it comes back again, it overshoots, and then it tries to come back again, and so it's a bit like that swing I described earlier, except this is happening with the three-dimensional sloshing about of stuff. So that's what goes on. That's if we have a tensile medium. Now, some people prefer a fluid medium for an ether. I think a tensile medium is the correct thing, because in light we know it's a transverse wave. So when light travels, it's not like the waves in the air that are pressure waves that move along. It actually does it this way.
I see. A horizontal motion, as it were?
Yeah, well, a transverse motion to the direction it's travelling. So light that's travelling from here to here wobbles this way.
Oh, I see.
It's like if we had a bit of string here, and I went like that, and a little wobble travels down there, right?
Yeah.
And that's what light is. And unlike if we had a column of air, and you go on the end, and a shock wave goes down.
Yes.
So if we think of it like that, as a tensile medium, my view is that this will explain all the things that happen in physics. Now, that it's got to explain quantum physics, it's got to explain relativity, and it's got to explain the cycles that we observe in the harmonics theory development that does explain the structures in the universe. So each of these three separate fields, they do meet at certain points and they do overlap a little bit, but largely they're separate disciplines. So people shouldn't think of them as competing with each other. Quantum physics works in its realm, general relativity works in its realm, and we'll do a separate session on this of the three limits of the universe.
But Newtonian physics doesn't work when you get down into the quantum realm.
No, because gravity doesn't have any effect there. Newton, incidentally, was perfectly well aware of this. He calculated, will gravity hold things together, and he worked out, not by a long shot. So he knew there was something else.
Yes.
And he knew, they knew about charge because they didn't know exactly what it was, but they used to rub things, you know, and you could pick up things with a bit of rubbed fur or something. You could pick up bits of paper and stuff. So they knew there was something else going on, and Newton did a bit of speculation about that, but he didn't make any attempt at a solution to it. He didn't think he got anywhere to that, but he just knew that matter had something else going on that hung it together.
Well, Ray, you gave a lot of examples. When you're looking at electricity, you're looking at the different kinds of waves, you're looking at photons, electrons, when you're looking at the distance of galaxies and planets and moons and so forth. But what I hear a common thread through all of these different examples that you mentioned is that they all seem to follow the same basic simple formulas that are reappearing time and time again at every different thing, at every different place, at every different scale.
There's a number of ways where that happens, yeah. So, for a start, the laws of physics, both the quantum ones and the general relativity and the general electromagnetic ones, are all wave equations. And they all have this property, as I said, that when you distort it, it tries to go back and it overshoots. So there's momentum. When you stretch it, it pulls back together. When you compress it, it pushes out again. So it's got a natural state that any disturbance from tends to oscillate, and that's the basis of cycles. So, in my view, all atomic particles are a special type of oscillation, which a little bit like the cup of tea, but not quite. It's in 3 dimensions, and it's transverse, so that we've actually got like layers of the wave outwards are doing this as a standing wave, and there's a sine wave of the velocities which is flipping backwards and forwards. And that's happening with what a particle is. Now that's been dealt with. Milo Wolf has written a book, and he's shown how, in actual fact, you can explain all the properties of an electron with this sort of a structure. In fact, when I first put my ideas about that on the internet, when I'd worked it out from harmonics theory, and I proposed that the electron could be this, I got an email from him saying, "Welcome to the club." The club was then 2, but since then it grew to a lot more. A lot of other people were thinking along the same lines, but he wasn't totally the first, but he was the first to prove that an electron could be satisfied by that sort of equation, and there have been a couple of others before. I would say, and he says that both Schrödinger and de Broglie both understood that correctly. That was what was going on.
De Broglie. Now, a lot of people know Schrödinger, but would you spell de Broglie, please?
D-E-B-R-O-G-L-I-E.
I think a few people are going to Google that when they hear this interview.
And and so he got a Nobel Prize for recognising the wave nature of matter and other things. Because he wrote in French and it was translated to English, not everything he worked out was fully adopted. And so there was another fellow that really understood it well, who came sooner. And that was just after Maxwell did his equations. What was his name again? Clifford.
Yep.
This Milo mentions this, that he said these wave equations allow special types of standing waves. These wave equations that Maxwell developed for electromagnetism, and he said that means they must exist. There's a general thing that physicists have that says what is not forbidden by the laws of physics is compulsory, right?
What is not forbidden by the laws of physics is compulsory.
Well, if you can make equations for it, that it's there, it can happen, and it will happen. And so basically, he said this has got to be what particles are standing waves of the atomic particles. And that they didn't even have atomic particles then, but he was proposing that matter was made of these standing waves of stuff.
Goodness!
Now he was way ahead of his time.
Yeah.
And I think he would have convinced everybody, except the poor fellow died quite young.
Oh.
But he left Clifford algebras, which were very valuable and used in a lot of the stuff. But that idea didn't catch on at that time. It wasn't until Schrödinger and de Broglie that they began to see the wave nature of matter. But they persisted with the silly idea of a duality. That's been a problem in physics because they've made a couple of fundamental mistakes. And we'll come to that. We'll have a talk at some stage about the Young's 2 slit experiment and light and what it means, and how they think they've shown it's got a wave nature and a particle nature. And they've made a mistake. They've shown it's got a wave nature, and they've misinterpreted, they've misunderstood the fact that there's no such thing as a travelling photon. emission of a photon is a more or less discrete event that happens to an atomic structure where an electron jumps orbitals or something like that, and there's a change in the structure which emits light. That light is then not independent of all others. It's just a part of the electromagnetic field. It's just a part of the waves in the ether. You kicked a little bit extra in, a little bit extra wobble, and those things just dissipate all across the universe. When at some stage somewhere else, enough energy arrives to kick another atom into a different state, and we call that absorption of a photon. But even though this event over here may be connected at the speed of light to this event over here, and therefore we know that light travelled between there and that this somehow caused that, it is not the same energy that was released here that was absorbed here. It's about the same amount, because at the same frequency it has to be the same amount under Planck's law, but it isn't the same energy. That one dissipated its energy across the universe, and this one absorbed it from across the universe. It so happens that this was just the extra bit that was enough to tip it over the edge.
Indeed.
And that doesn't happen everywhere. There were lots of other atoms that weren't affected by that because the background radiation wasn't doing it. And so that's one fundamental misunderstanding that's in physics that causes a number of wrong thinkings about the particle nature of matter. And
I can understand how it appeared to be traveling.
Yes, it looks like it.
It leaves some here and it shows up here, but it's not the same as.
Such a clever person as Feynman was to say light is a particle. I say he's quite wrong about that. He was right about a lot of things, very clever fellow. Him and Wheeler began to look at an electron, and they worked out an electron structure can be explained as a wave emitting from it outwards, forwards in time, and another wave emitting out from it backwards in time. Now, I wouldn't say you've got a way of going outwards, backwards in time. I'd say you've got a way converging on it forwards in time, and then passing through the centre going outwards again. Now, they arrived at that as things that happen to an electron. If they'd made one little further step of saying that coming forward in time, and also then saying that's not what happens to an electron, that is an electron, there is nothing else, then they would have arrived at what Maya Wolf did for the model of the electron, and they would have done it a lot sooner. So, clever guys, and the physics they developed is fairly widely accepted today, but they didn't quite get it. They didn't quite get it. Yep. There's a possibility to change that, to recognise that it is what an electron is, there's nothing else.
Well, you're explaining that there is a way to resolve the conflict between the particle versus wave. I mean, because this has been the long-standing question.
It has, yeah. And it's behind a number of things where a lot of modern books like to focus on the unintelligibility of physics and the weirdness of it. And it's not weird. There's no weirdness. In my view, there's no weirdness. These other experiments that Einstein tried to battle with Bohr, because Einstein didn't believe there would be weirdness. He believed, his famous thing, God does not play dice with the universe. Yeah. And he wanted to show that it was following laws that happened. And he couldn't quite get it because he couldn't find the right way through. And so there were these experiments called the Epr Paradox, and there's a number of experiments around that. And when they did the experiments, some of the early experiments tended to show that Bohr was always right. And Einstein was wrong. But in actual fact, I believe Einstein was always right, but Bohr's explanation was that you couldn't understand beyond the point, but Einstein wanted to, and you can. I can find ample cases where you can go beyond that point that have happened since Einstein's time. And
a lot of times when we do go beyond that point, we find that the answers are in fact intelligible, even though they seem to be beyond our grasp. We build models that we can understand, and we tend to hang on to them. But very often we find out that the things, and sometimes it's just easy to understand once you know how.
Yeah, the problem is with models is it's very easy to start thinking they are reality. And many physicists and astronomers and so on, cosmologists, think their model is reality. And when something doesn't agree with their model, they reject the data. Now, you can have suspicions about data for that reason, but you've got to check it out. And if it stands up, you've got to accept it, and you've got to accept your model's wrong. and there's a lot of things been wrong. So in cosmology, they keep adding on new bits and pieces, you know, to the model to try and make it work. And there's been some good. There was an Australian guy who wrote some good papers that showed that every time they studied a new area, they had to invent one new thing to put into the cosmological model to explain it. And which was one of the physicists said this, one of the mathematical physicists said this. He said, how many parameters have you got in your equation? And the guy said how many he had, and he said, oh, with 7 I can make an elephant, and with 6 I can make an elephant, and with 7 I can make it dance, or something like that. And so you don't, if you've got that many parameters, you can make it do anything.
Yeah, you modify it that much,
yeah.
It isn't the same thing at all.
And so in my in the harmonics theory, there's one axiom, right? Mm-hmm. That's it. We have to then work out the relationship of that to the universe in terms of scale, and it turns out that the universe is vastly larger than what the Big Bang people think it is, and vastly older.
Very often that's been revised on how big the universe
keeps on
is.
going up, doesn't it?
Yes, it does. It certainly does.
It started going up from when I was born to 6,000 years to, you know, to billions of years. So.
Well, we got to know when to let go of what we were holding on to in order to be able to hold on to more and find out that what we're holding on to is real. I had a fellow that was showing me a genuine Indian tomahawk he had. Tomahawk is Native American axe, of course. And he said when he found it, the handle was missing, and since then he had to replace the head. But he guarantees its authenticity.
Yeah, my grandfather used to say that about his hammer.
So when you change it that much, it isn't it.
Yeah.